Jai Hind. Myself Ravindra Kumar, AP in EN Department, Ajay Kumar Garg Engineering College, Ghaziabad. Today I am presenting on the topic transformer phasor diagram under the subject Fundamentals of Electrical Engineering. In this topic is covered under Unit 3 of this subject. Subject code is BEE 101 for the odd SEM, that is first SEM, and it is BEE 201 for even SEM, that is second SEM, for the students who are taking this course in first year classes of AKTU, that is Abdul Kalam Technical University. So under this topic, today I will be discussing about the phasor diagram of a transformer on no load condition and on load condition. In both the cases, the phasor diagram of transformer will be discussed under this presentation or discussion. So if we see it, first we discuss about practical transformer, or we also call it a transformer. Practical transformer or transformer, that means same thing, that represents transformer. So I can write it practical transformer or a transformer or non-ideal transformer. Anything can be written, practical transformer or non-ideal transformer or transformer. So this practical transformer or say non-ideal transformer or transformer, that indicates same thing. So if we take it on no load condition, so no load means when secondary circuit is open circuit of the transformer, there is no load connected at secondary side. So when this is the condition, that time no current will be there at secondary side and no power will be there at secondary side due to no current at secondary side. So if we see it here, this is the symbolic representation of single phase 2 winding transformer. We can write it single phase 2 winding transformer. Transformer is written in short as this. This is representing transformer. So this is the primary winding to which we are connecting this supply input, and this is the secondary winding from where we are getting power output from the transformer. Primary winding is having number of turns N1 and secondary winding is having number of turns N2. So for all the quantities of primary, we are using 1 as subscript with the quantity, and for secondary winding quantities, we are using 2 as subscript with the quantity for representing whether it is primary side quantity or secondary side quantity. Other than this, this phi represents flux in the core, which is mutual flux, which is linking with both the windings, primary as well as secondary. This is input voltage V1 to the primary side. This is I0, no load primary current. I0 is no load primary current. Since secondary is not having any load connected there, so that's why no current at secondary. That time the primary current is no load primary current, which is represented by I0. Now, other than this, when secondary circuit is open circuit, that time the induced EMF E2 in the secondary will also be equal to terminal voltage of secondary, that is V2. Due to when no current is there at secondary side, there will be no voltage drop, and when there is no voltage drop, that time whatever is the induced EMF in secondary, that is this E2, same will be the terminal voltage V2 across secondary terminals. So this will be the condition. Other than this, primary, that is having no load current, I0. Now, if since it is a practical transformer or say non-ideal transformer or transformer, whatever we call it, the following effects will be there. Now the exciting current or say no load current, exciting current is also known as no load current in the primary. It will be having two components. One is magnetizing component, which is I phi. This is represented by I phi. And another one is IC, core loss component. This is IC, core loss component. Now this magnetizing component I phi, it is in phase with flux, while the core loss component IC, it is along V1 dash, which is minus E1. V1 dash is the voltage drop in primary winding, which is equal to E1, induced EMF in primary, E1 in magnitude, but opposite to E1 as per Lenz's law. That's why V1 dash we can write equal to minus E1. So E1 is the induced EMF in primary and V1 dash is the voltage drop corresponding to that, which is equal to E1 but opposite to E1. That's why minus sign is written with this E1. We will discuss it in detail in the phasor diagram, all these topics, all these parts. So now if we move further, we can conclude some results from the phasor diagram. IW, this is also known as IC, core loss component of no load primary current. This is I naught cos phi naught, while another component is I mu, that is also known as I phi, magnetizing component of primary no load primary current. This is given by I naught sin phi naught. So I naught, no load primary current, that can be written under root of IW square plus I mu square, or under root of IC square plus I phi square. Since IW can also be represented by IC and I mu can also be represented by I phi. And cos phi naught will be given by IW upon the I naught. Cos phi naught, from here we can say cos phi naught will be given by IW upon I naught. This is I naught basically, or this can also be written as IC upon I naught, where cos phi naught is no load power factor of the transformer. Phi naught is no load power factor angle. So cos phi naught is IC upon I naught. This is the phasor diagram of transformer at no load condition. This is maximum flux, which is in the core. This is I mu or I phi, magnetizing current, which is in phase with flux. This is IW or IC, which is representing core loss component of the no load primary current, and the phasor sum of I phi and IC, that is I naught, no load primary current. So we can write I naught is phasor sum of I phi and IC. E1 and E2, they are the induced EMF on the two sides which are lagging by 90-degree angle from the flux. So they are lagging by 90 degree from the flux. That's why this is clockwise angle from flux to E1, E2, so that it is representing that E1 and E2 both are lagging by 90 degree from flux. And this is V1 dash, which is the voltage drop in primary winding equal to E1 in magnitude but opposite to E1. So that's why we can write V1 dash equal to minus E1. That can be written. Angle phi naught, which is no load power factor angle, and power factor due to this cos phi naught, that is no load power factor. Other than that, core lossage, that can be written V1 I naught cos phi naught. Since IC is core loss component, so V1 into IC is core lossage, and V1 I naught cos phi naught, that is also core lossage. So this is V1 IW or V1 IC, unit is watts for core lossage. And the magnetizing volt ampere, that is reactive volt ampere, that will be equal to V1 I naught sin phi naught, or V1 I mu, or V1 I phi. VAR, volt ampere reactive, which is the unit of reactive power. So that way these are some components which will be there in the transformer at no load condition. So if we describe it or we discuss it in detail, that what will be the phasor diagram of a transformer at no load condition, so we can discuss it in the next slide, that we can see how it will be drawn. And before that, if we take some numerical related to it, like this numerical, a transformer takes a current of 0.8 ampere when its primary is connected to a 240 volt 50 hertz single phase supply, with secondary being open circuit. That means this is the no load condition of the transformer since secondary is open circuit. That time the power absorbed is 72 watt. So we are to determine iron loss current, that is core loss current also we can say, and the power factor at no load and magnetizing component of no load current. So if we see the solution for this, no load current is given in the question, I naught 0.8 ampere, that is this current given here in the question, 0.8 ampere, this one. Then core loss, that is also given 72 watt, that is this. Power absorbed 72 watt, that is representing core loss at no load condition. Since current is very small, so copper losses will become negligible small or very small value, so that can be neglected, and that's why 72 watt will be basically representing core losses. Now core loss is given by V1 I naught cos phi naught, that we have seen in the previous slide, that core losses are V1 I naught cos phi naught. So from that, if we put the value here, we will get cos phi naught, which will be P core loss upon V1 into I naught. So putting the values here, 72 is P core loss and V1 is 240, that is given 240 volt voltage, primary voltage, and I naught, that is 0.8 ampere, that is also given this one. So this no load power factor comes out as 0.375. Now we want to find core loss component or iron loss component of no load current, that is given by I naught cos phi naught. This is IC, core loss component of no load current. So I naught is 0.8, cos phi naught is 0.375, that we have already found. So this comes out as 0.3 ampere. Similarly, magnetizing component of no load current, that is I phi. This can also be written I phi. So this is given by I naught sin phi naught, that we have seen in the previous slide from this phasor diagram. I naught sin phi naught becomes I phi. I naught cos phi naught is IW or IC. So from this, I phi becomes I naught sin phi naught, and I naught is 0.8 ampere. Sin phi naught can be calculated since cos phi naught is already calculated 0.375. So sin phi naught can be calculated from the relation sin phi naught equal to under root of 1 minus cos square phi naught. So after finding this value of sin phi naught, if we put it here, we get I naught sin phi naught equal to 0.74 ampere, which becomes magnetizing component of no load primary current in this case. And this magnetizing component of current, that is responsible for setting up of magnetic field and flux in the core of transformer, while core loss component of no load primary current, that represents for core losses which are taking place or which are occurring in the transformer core. So if we discuss this phasor diagram completely at no load condition for a transformer, so we can discuss it, how it will be there. Transformer phasor diagram. At no load. So secondary side will be open circuit. That means no current will be there at secondary side. So what we do first we draw both the axis, horizontal as well as vertical axis. On horizontal axis we take flux. Since flux is taken as phi equal to phi max sin omega t, and that means it is along reference. Since with omega t there is no angle, we can also write it as phi max sin omega t plus 0, and that means there is no angle with omega t. That's why this is along reference. Now the induced EMF of the two sides, they will be lagging by 90 degree from the flux. That already we have seen in the recording when we have derived the induced EMF equation of the primary and secondary, there we found that induced EMF on the two sides, they lag by 90 degree from the flux. So this is 90 degree lagging from flux. Since the expression for induced EMF we found, E1 is given by E max 1 sine omega t minus 90 degree. Similarly, E2 is given by E max 2 sine omega t minus 90 degree. So that's why induced EMF E1 and E2, they are lagging by 90 degree from flux. Now there is no current in secondary, so that no voltage drop in secondary side. So E2 and V2 will be equal. That already we have discussed. So same thing will again happen here. If you see the symbolic representation of transformer this time, it will be like this. This is primary side and this is secondary side. Secondary is open. Here the voltage supply connected V1 in the primary, induced EMF E1 in the primary, and secondary induced EMF is E2, terminal voltage is V2, and it is secondary open circuit. So I2 will be 0 here in the secondary due to open circuit in secondary, and corresponding to E1 we have the voltage drop in primary V1 dash, which is equal to E1 in magnitude but opposite to E1. That's why we take it minus E1. So if we take it in this phasor diagram, we can also take it that this is V1 dash, which is minus E1. Now other than that, I5, that is magnetizing component of no load primary current, that is along flux. There is a reason for this also, why it is along flux, that I will discuss after this. And another component is IC, which is core loss component of no load primary current. This is along V1 dash. Why it is so? I5 is given by V1 dash upon X5, where X5 is magnetizing reactance, which is of inductive nature. And we know in inductance, the current lags from the voltage by 90 degree. That's why I5 is lagging from the V1 dash by 90 degree, that way. This is lagging by 90 degree. IC is given by V1 dash upon RC, where RC is core loss resistance. And we know in a resistance, current and voltage are in same phase. That's why IC is along V1 dash. That is the reason for this. Now further after this, phasor sum of IC and I5 will be I0, no load primary current. Since IC and I5 both are the component of I0. Now the angle between V1 dash and I0, that is no load power factor angle phi naught, and the cosine of this angle phi naught will be no load power factor cos phi naught. Now after this, if we take the voltage equation of primary side, V1 will be equal to V1 will be equal to V1 dash, which is minus E1, plus I0 into R1 plus JX1, where R1 is primary winding resistance of the transformer X1 is primary winding leakage reactance of the transformer. So if we include this in the phasor diagram, according to this equation of primary side voltage equation, what we have, this is V1 dash, this line is representing V1 dash, I naught R1, that is the voltage drop in primary winding resistance, so that will be in phase with I naught. So we can take it I naught R1 here for addition with V1 dash. This I naught R1 is in phase with I naught, so that's why we have taken I naught R1 parallel to I naught. Now next is I naught X1, that will be 90 degree leading from I naught, reason being X1 is primary winding leakage reactance which is of inductive nature, and in inductance voltage leads the current by 90 degree. So I naught X1 will be leading from I naught by 90 degree. So that way if we take it, so this is I naught R1, from this we have taken leading I naught X1 by 90 degree. This is 90 degree angle, anti-clockwise, representing the leading quantity. I naught X1 is this, and now the phasor addition of V1 dash, I naught R1 and I naught X1, that becomes supply voltage V1. So this is V1. So that way it is a phasor diagram of a transformer or practical transformer or non-ideal transformer at no load condition. Next we discuss about the phasor diagram of a transformer at load condition. So if we see it, what will be the changes that we can see now? When the practical transformer is connected with some load, or a transformer is connected with some load, that means secondary circuit is connected, secondary side of the transformer is connected with load, that is shown in the diagram here. This is the load impedance connected to secondary side, this is primary side, this is the voltage supply connected to primary, E1 is the induced EMF in primary, E2 is the induced EMF in secondary, V2 is the terminal voltage across secondary, that is also known as load voltage since load is connected across the secondary terminals. I2 is secondary current. Primary current will now be I naught, that is no load primary current, plus I1 dash. I1 dash is load component of primary current. I1 dash is known as load component of primary current. That is, I can write it here. I1 dash is load component of primary current. How it arises, that will be discussed in this load component of primary current. N1 are the number of turns on primary, N2 are the number of turns on secondary. Phi is the mutual flux which is linking with both the sides, primary as well as secondary side. So now when supply voltage V1 is connected to the primary side of the transformer, then primary current I1 that passes through the winding and that produces maximum flux phi max in the core of transformer. When the secondary winding of the transformer is connected with some load, the secondary current also passes through the secondary winding, that is I2. The secondary current I2 that sets up its own MMF, which is N2 into I2, and due to its own flux phi 2, which opposes the main flux or the primary flux, then the resultant flux due to it and the primary induced EMF is also decreased. Resultant flux and primary induced EMF both are decreased. The resultant flux now becomes phi max minus phi 2. Phi max is the flux which is due to primary and phi 2 is the opposing flux of secondary as per Lenz's law. Since as per Lenz's law, effect opposes the cause, so phi 2 which is the effect due to the variation in primary flux. So phi 2 opposes phi max. That's why the flux in the core that is reduced and it is now phi max minus phi 2. But we want that core flux should remain same so that induced EMF on the two sides of the transformer should not be affected. So the flux in the core to remain same, what should be there? Some additional flux should be generated or created from the primary side, so which will neutralize phi 2 and the main flux will not be affected, it will remain same. So if we see it further, this is phi 2 which is the secondary flux which is opposing main flux phi, and corresponding to it, primary winding is taking additional current from supply, which is load component of primary current I1 dash, and that is generating additional flux phi 1 dash, and this is equal to phi 2, phi 1 dash equal to phi 2, but opposite to phi 2 also, so that phi 1 dash and phi 2 neutralizes each other or cancel out each other, and main flux remains as it is, that is not affected due to it, and that we want. So that's why this additional current I1 dash, which is load component of primary current, that is drawn by the primary side when the secondary side is connected with some load impedance. If there is no load impedance connected at secondary side, or in other words, we can say secondary side is open circuit, that time no load, that time primary side will not take any load component of current. That time only the no load primary current will be there in the primary side when secondary side is open circuit or no load condition. So if we see it further, supply system draws more current from the primary winding due to the difference between supply voltage and induced EMF, and it increases until the original value of flux is obtained. Suppose the additional primary current I1 is I1 dash, which is load component of primary current, that already we have discussed in the previous slide, and now this current I1 dash is in antiphase with I2, so that it can neutralize the effect of I2 flux. Current I1 dash is known as load component of primary current. Current I1 dash sets up its own flux phi 1 dash in magnitude, and therefore MMF N1 I1 dash and MMF N2 I2 and the flux due to them, they cancel out each other, and we can say that the magnitude and phase of load component of primary current depends upon the type of load. Now the net flux passing through the core remains constant, since whatever is the flux created by secondary current, same amount of flux is also created by additional primary current, which is known as load component of primary current, and due to this the additional flux of primary plus the flux due to secondary current, they are opposite to each other and equal to each other, they cancel out each other, so the main flux is not affected, that remains same or constant. So core flux remains constant whatever is the load connected across secondary side, and if we neglect primary and secondary leakage fluxage. So that is the process which happens, or that is the phenomena which happens in a transformer when some load is connected across secondary side. So if we take it in phasor diagram, we can go for phasor diagram of it. First we take both the axes, horizontal and vertical axis. Now at horizontal axis we take flux, which is main flux of the core. Induced EMF on the two sides, E1 and E2, they lag by angle of 90 degree from flux, that already we have discussed why. So this is E1 and E2, they are lagging by 90 degree from flux. Now secondary side voltage and current. V2 is the terminal voltage of secondary, that is taken at this side, V2. Suppose the load impedance which is connected across secondary of transformer, that is of lagging power factor nature. So that time the current in the load impedance I2, that will be lagging by some angle from V2 load voltage. So I2 will be lagging by some angle from V2. So I2 will be here, somewhere here. So now the secondary side voltage equation will be given by E2 equal to V2 plus I2 into R2 plus JX2, where V2 is the load voltage or terminal voltage of secondary of transformer, E2 is the induced EMF in secondary, I2 R2 is secondary winding resistance voltage drop, I2 X2 is secondary winding leakage reactance voltage drop, and the phasor sum of all these will be E2. That is V2 plus I2 into R2 plus JX2 is E2. So if we take it in phasor diagram, I2 R2 will be in phase with I2 as per earlier discussion. So I2 R2 will be along this side parallel to I2, and I2 X2 will be leading by 90 degree from I2. That already we have discussed why it is so. Same thing again. So I2 X2 will be this, leading from I2 by 90 degree. So if we see it, this angle is 90 degree. This is I2X2 and the phasor sum of V2, I2R2 and I2X2, that is E2. So this is secondary side phasor diagram of the transformer at load condition. Now at primary side we have I0, no load primary current, which is having two components, I5 magnetizing component and core loss component IC, and the phasor sum of these two, that is no load primary current I0. That already we have discussed in the previous case when we have discussed the transformer phasor diagram at no load condition. Now due to the current I2 in secondary, primary winding draws additional primary current, that is I1 dash, which is known as load component of primary current, that we have discussed in the previous slide, and that is in anti-phase with I2 or in phasor opposition of I2. So from I2 we will take anti-phasor I1 dash, that will be this is I1 dash, load component of primary current, and now the phasor sum of I1 dash with I0, that becomes resultant primary current I1. So if we take this using parallelogram method, so this is like this. This becomes I1. Now further after this, if we take the voltage equation of primary side, so we can write V1 equal to V1 dash plus I1 into R1 plus JX1. Like earlier also in no load condition we have discussed such type of equation of primary side. Here the change is now I1 is there in place of I0. In no load condition this was I0, but now it is I1 since it is loaded condition of transformer. V1 dash is equal to minus E1, which is the voltage drop equal to E1 but opposite to E1. That's why V1 dash is minus E1. I1 R1 is primary winding resistance voltage drop. Since it is a practical transformer or a transformer that is having winding resistance and leakage reactance, I1 X1 is primary winding leakage reactance voltage drop. So when all these voltages are added up, phasor sum of these are taken, that time we get supply voltage V1 in the primary. So if we take it in the phasor diagram, V1 dash, that is opposite to E1 and equal to E1, so that we can take here V1 dash is this. This is V1 dash minus E1 opposite to E1 and equal to E1. I1 R1, that will be parallel to I1 since I1 R1 is in phase with I1, and I1 X1 is leading by 90 degree from I1 R1 or I1, anyone we can say, since I1 R1 is in phase with I1, that's why it is so. So this is I1 X1. This angle is 90 degree since I1 X1 will be leading by 90 degree from I1 or I1 R1, anyone, since I1 R1 and I1 also are in same phase. So now the phasor sum of V1 dash, I1 R1 and I1 X1, that gives us primary side applied voltage of supply, that is V1. So that way it completes the phasor diagram of a transformer at load condition, that V1 is phasor sum of V1 dash, I1 R1 and I1 X1. So that's how we can draw the phasor diagram of a transformer at load condition. Now in this also there may be different conditions of load. It may be lagging power factor load. Here it is lagging power factor load since load current I2 is lagging from load voltage V2 by some angle phi 2, suppose. Or it may be leading power factor load. That time load current I2 will be leading from load voltage V2, and accordingly again we will repeat these steps, somewhat shifting of these different voltage and currents will be there that time when load current I2 will be leading from load voltage V2 in case if it is leading power factor load connected across secondary of transformer. Or third case, it may be there if it is a purely resistive load connected across secondary. That time load current I2 and load voltage V2 will be in same phase or along same line. And accordingly, again, there will be some shifting of voltage and current phasors in this phasor diagram, and then we can draw the phasor diagram for the different conditions of load, that is lagging power factor load, leading power factor load, or resistive load, the purely resistive load which is having unity power factor. So that's all about this. We have discussed under this phasor diagram of a transformer at no load condition and then at load condition. So this completes this topic. In the next discussion, we will be discussing another topic related to losses and efficiency of transformer and the condition for maximum efficiency of a transformer and the numericals related to efficiency of transformer. That's all. Jai Hind.